Hello everyone, it's me, Mr. Younger again. I decided to make a video about the derivations of CP and CV, that is the molar specific heat at constant pressure and molar specific heat at constant volume for an ideal gas. So I'm going to share my iPad screen with you and then we'll get started. So let's go ahead and share the screen. So in order for us to pull out this derivation or pull off this derivation, we need a few specific facts. So one of them is the uh, first law of thermodynamics, and that says that delta E internal, the internal energy, the change in internal energy, is equal to the heat added minus the work done by the system. That's the way we use it here in physics is Q minus W because we're talking about the work done by the system instead of the work done on the system. So we have that. We also have the ideal gas law, which is PV equals nRT. Of course, there's also PV equals nKT, but we're not going to be using that this time. So now that we have what we need for the derivation, I'm going to go about doing it. So first thing we notice, and you can see this from any table, any textbook, I showed it to my students, but basically if you look at the specific heat of an ideal gas in the normal units that we're used to, which is like calories per gram Celsius degree or joules per kilogram Celsius degree, they show no rhyme or reason. In other words, if you look at the specific heat of an ideal gas that's monatomic, one monatomic gas can have a very different value for CP or CV than the other. Same thing for diatomic, same thing for polyatomic. However, if you make a jump from specific heat in terms of joules per kilogram Celsius degree or calories per gram Celsius degree and switch them to molar specific heats, it turns out that there's a very nice pattern that emerges and you get a very specific value, more or less, for monatomic gases. You get a different specific heat, molar specific heat for a diatomic gas, and so on and so forth. So that's what we're going to try to do here. So first off, I want to introduce you to what the specific heat is in terms of molar specific heat. So we also have this definition CP, which means that, notice it's capital, but it means that it's the specific heat of a particular gas at a are under conditions of constant pressure. And the units for that should be equal to, in one case, for instance, joules per mole Celsius degrees. And similarly, we have another one, CV, that's the molar specific heat at constant volume, and that too will have units of joules per mole Celsius degree. Uh, and that is starkly different from CP, the lowercase version, which has units, say, of joules per kilogram Celsius degree, or calories per gram Celsius degree, and CV, again lowercase, also has joules per kilogram Celsius degree, or calories. Those are lowercase calories in case it looks different. It's hard to tell that the C is capitalized or not, but it's not capitalized. In this case, it'd be calories per gram Celsius degree. So in order for us to figure out how to do it, or how to actually make this specific heat, I'm first off going to tell you that the specific heat at constant pressure in molar values is actually equal to the molecular weight of the gas that you use times the specific heat at constant pressure in the typical units of joules per kilogram Celsius degree or calories per gram Celsius degree. Similarly, the specific molar specific heat at constant volume is also given by the molecular weight times the lowercase c sub v. So those are how you actually go about calculating the specific heats, the molar specific heats. Now I want to make sure you understand how we would use them. We did know, for instance, that when we were using the normal specific heat, the Q was equal to mc delta T. But in this case, we can't use that anymore. So I'm going to point out that Q And I'll subscript it P so we'll know that I'm talking about in the event that Q is done with a constant pressure, then the amount of heat QP goes into changing the temperature by this equation. QP is equal to N, which is the number of moles, times capital CP times delta P, and QV. Again, this is the heat added to the system, say, at constant volume, but we're doing it in terms of molar specific heat, so it'll be N times CV delta T. So those are some equations we'll be making use of to make sense of this. So first thing I'm going to do is take the first law of thermodynamics and apply it to the case of QV. So in the first law of thermodynamics, we have delta E internal is equal to, oh, I just remembered another thing I wanted to give you guys before we started this, but that's okay, I'll wait. The delta E internal is Q minus W, as we said, but if we're considering this in the case of constant volume, then this is going to become delta E internal is equal to Q sub V. And it's only Q sub V because work is equal to the integral of P dV. But dV equals zero, so we basically get QV minus zero. Similarly, we can take the delta E internal from the first law of thermodynamics, and again, it's equal to Q minus W, but if we do it under constant pressure, then we end up getting QP minus P delta V, because if the pressures are constant, the integral P dV just becomes P times the integral of dV, and therefore it's just P times delta P. Now, both of these cases, we have the internal energy being equal to the same thing. So we can, in principle, I should have put, yeah, we can, in principle, equate them and remove them as necessary. So what we're going to do is we're going to calculate basically what QP is and in terms of QV. So if I solve the second equation for QP, I would say QP is equal to delta E internal. And then, of course, pulling the P delta V to the other side, I end up getting P delta V. So we have now a plus. And we can also take the equation for delta E internal for constant volume and replace that delta E internal in it. So if I combine this equation and this equation, I get QP is equal to QV plus P delta V. Now, if I choose to solve for QP minus QV because I know where this is going to go, then I can actually get a result that's starting to look helpful. So I'll consider what QP minus QV is. The QP minus QV will actually become just P delta V. At this point, I'm going to use the idea that PV equals in RT. Now, this lets us know that, for instance, well, let's do it this way. This lets us know, for instance, delta V is equal to N times R times delta T over V, or excuse me, over P, like that. So I can now plug in that delta V in the formula that we had just worked out, and from that, we're going to get QP minus QV is equal to P times NR delta T over P, R QP minus QV is just equal to N times R times delta T. Now, if we go back to calculating what QP and QV were in terms of the specific heat, then we get one of the major conclusions that we needed. So QP is going to become NCP delta T. So I'm going to say N CP delta T minus QV, which is going to become NCV delta T. And then we still have NR delta T. At this point, you can see that I could divide through by delta T, and all those would disappear. And then I could divide through by N, and all these would disappear. So I get our first major result, and that is that CP minus CV is equal to R, and that is a important result. I'm going to box it off like this. So now we've got it. Now that I've got that, I know that the molar specific heats for an ideal gas actually differ by an amount R, and I can use another equation, which I meant to include at the top, but didn't, but I'm going to put it up there now, and that is the internal energy, or the change in internal energy for a monatomic ideal gas is delta E. Oh, yeah, I'll leave it written in red so it won't converge with the other stuff. So delta E internal is equal to, again, this is for a uh, no, this one's for a monatomic ideal gas. So it's 3 halves N times R times delta T. So now I can make use of that as well, and that will come in handy a little bit later. So now what I'd like to do is try to actually compute what is the actual C sub V. So if I want to try to calculate the C sub V, I can go ahead and take delta E. Oops, I should write back in blue now. I can go ahead and take delta E internal is equal to what we found earlier under constant volume was that delta E internal is just equal to Q at constant volume. So if we again use this for an ideal monatomic gas, then I'm going to say 3 halves N times R times delta T is equal to N times CV times delta T. And again, we can see that the delta T is common to both sides and therefore can be divided out. And the N is common to both sides and can be divided out. Again, making the normal assumptions that you do with algebra, that the thing we're dividing by cannot be zero. So we're not considering no changes in temperature, nor are we considering 0 moles. So with all of that, we can finally reach this conclusion, which is that CV is equal to 3 halves R, and this is for an ideal monatomic gas. Okay, so that's another important result for us. And we could, of course, just go ahead and plug that in CP minus CV equals R. And I think you would all conclude that if we did that, CP would obviously be equal to, uh, CP would obviously be equal to 5 halves. But I'm not going to do that. I'm going to show you that if we calculate it sort of the same way we did here, we will also get CP is equal to 5 halves R. So now I'm going to take the first law of thermodynamics for constant pressure, and that is delta E internal turned out to equal QP minus P delta V. So again, I can plug in the conditions for an ideal monatomic gas, and I'll get 3 halves N R delta T is equal to N CP delta T minus P delta V. Now, using PV equals nRT, we can actually reach the conclusion that delta V would be nR delta T over P. So if I plug that in, I get this 3 halves N R delta T is equal to N CP delta T minus P times N times R times delta T over P. Now you can see that the P's cancel out here. And then we can ultimately also see that the N and each of the delta P's are going to cancel out as well. So what we'll get is something quite nice after that. We get 3 halves R is equal to CP minus R, which means CP is obviously equal to 5 halves R. And that's it. That's how we make the conclusions about CP and CV, their difference, as well as what they are for an ideal monatomic gas. So hopefully that clears up why we use these formulas and shows you how to get it, not unlike the derivation that your textbook author has. So I hope that helps. That's it. Have a good day. Bye bye.